afternoon, every one of you. So here we are after finishing out the session number 8, which was all about how we will be moving towards railway developments. Now it's time to see what challenges we will be having and what opportunities we will be gathering in nuclear defense and aerospace sector. So I welcome you all back. We will be having really great dignitaries amongst us today for session number 9. So let's begin and commence with session number 9. The topic that we are covering is challenges and opportunities in nuclear defense and aerospace sector. To conduct this session, I would like to invite our moderator for session number 9, Dr. Kamchi Mudali, Vice Chancellor from Homi Bhabha National Institute. Dr. Kamachi Mudali, please be on stage. We are really having honor to have you amongst us, sir. Can we have a big round of applause for him? He will be conducting this wonderful session. And now it's time to invite our first panelist, Mr. Raghvendra Tiwari. He is outstanding scientist and Associate Director from Materials Group, Bhabha Atomic Research Center. A big round of applause for him, as these people really work very hard to bring something new and innovative amongst the globe. And our second panelist for today is Dr. Gunsekaran, Scientist F, Naval Material Research Laboratory. The topic we are covering, I would like to repeat myself, the topic we are covering under session number 9 would be challenges and opportunities in nuclear defense and aerospace sector. We are having really big dignitaries, guests, because they come from science background. They're having great and immense amount of knowledge, and definitely this session would be really great to hear out. So without wasting any time further, I would like to request our moderator and panelists to start over the discussion for the day.
Good afternoon. A warm welcome to this panel on challenges and opportunities in nuclear, defense and aerospace sectors. And I have two eminent and experienced professionals, Dr. Raghvendra Tiwari from Bhabha Atomic Research Center and Dr. Gunsekaran from Naval Materials Research Lab. He is from Nuclear Department, he is from Defense, DRDO, Defense Research and Development Organization. And to begin with, I would like to say that today for our nation, energy and national security are like two eyes. They are very important. We are talking about the industrial progress that we should take in the next, 50 years. Or by 2070 or so, when there is a net zero carbon is going to be predicted as by all, we need to also have to produce tremendous energy, and producing energy will also produce a lot of carbon dioxide to the atmosphere. So the whole country has to progress in atomic energy. Energy is very important, and nuclear energy today it is contributed only to about 3%. And if we are going to increase the nuclear energy from 3 to, let us say, by 2070 to 20%, and that is going to be involving very good quality, large volume of stainless steels. And coming to the national security front, the defense and aerospace, there is going to be a porous border that what we have today with the Chinese intrusion in 2020 in the Ladakh region has made us to work more and more to enhance the combat readiness in the border and increase our equipment production and the combat readiness with both defense and aerospace sectors. So either improvement or increase in the energy production or in the national security with defense and aerospace, materials play a key role. And stainless steel being one of the primary alloy that is being used next to steel and aluminum in many applications plays a very key role in these strategic applications. Particularly, if you look at the atomic energy or the nuclear energy department, where I am also belonging to, and I served there nearly now 40 years, stainless steel is the primary alloy that is used in the construction and application and utilization of all type of nuclear power plants in the country. And similarly, if you go to the defense and aerospace, stainless steel plays a very major role. If it is aerospace, it is useful to the landing gear, superstructure, or the aero engine components. If you are talking about the other combat readiness equipment, stainless steel has got a major role to play. This is mainly because stainless steel is a versatile alloy. It's a recyclable alloy. It is an environment-friendly alloy that can be used for various applications from very high temperature to low temperature and with an adequate strength, ductility, and corrosion resistance. So with all its attractive property, with all its outstanding nuclear or defense and aerospace applications, today stainless steel plays a key role. So what is that is going to be the challenge? What is that is going to be the opportunity for future? Today we are almost, if you ask me, nearly 20 to 30% of the primary material that is used in defense aerospace and the aerospace, nuclear defense and aerospace, it is primarily stainless steel. So I would like to know from the specialists with me in the panel, what is the challenge today and what are the opportunity that is India is having and the industries, the stainless steel industries have today for the future. So let me begin with Dr. Raghavendra Tiwari. Dr. Raghavendra Tiwari is the director of the materials group at Baba Atomic Research Center. He has nearly 30 years of experience in the materials field, and being a mechanical metallurgist, he is well aware of the use of stainless steel for a tremendous application in the nuclear energy field. I would like to request him to tell what are the challenges and what are the opportunities that we have from today. Welcome, Dr. Tiwari.
Thank you, Professor Kamachi Mudli. Working in DAE, particularly in BRC, because BRC in a broader sense uses the first element of the periodic table, hydrogen, to the heaviest element, uranium. The entire periodic table is spanned in BRC, and we were fortunate enough to have people who guided us, and we are the only probably department who are using, I think, 98 elements out of the 108 natural elements are being used in DAE. Now, if I come to the stainless steel, if I take the ternary diagram with the nickel on one edge, chromium on other, and iron in other, so this was maximum utilized in DAE. If you go on the nickel-rich side, you have a super alloys, you have a haste alloys, you have pneumonic alloys. If you come on the chromium-based alloys also, there are some few alloys were used. But among them, the most one is the stainless steel. Rather, when we join our BRC through training school, one special course is given on the stainless steel. And if you allow me, so let me tell you something, that how the stainless steel were discovered. This is the version given by my professor while teaching that. See, the stainless steel has a hand of a lady behind it. Probably you do not know that. See, there was some old-time curious people who wanted to develop some steel. Okay, so one scientist, I'm actually forgetting his name, so I will not name them. So he was very curious on developing various steel. So he was selling the land, his mansion, his all the belongings to make some funny steels. So his wife used to get very angry with him. So what he used to do when the lady used to go for the church on every Sunday morning, he used to do the experiment to see the part in the basement, of course. So one day he was adding what now we know is a ferrochrome in the steel. And before that day, unfortunately, his wife came early. So what he did, he threw the half-cooked material in the backyard and ran away from there. The next day morning when he has gone, he saw this is a very shining kind of the iron was there. This was his aim. Because those days chemistry was not very clear. So he thought by mistake something else has happened, it must be silver. And that is why it came up. Because he had no intention of adding 12% chromium. This all was luck. And that gives the origin of stainless steel. As you know, the term stainless steel called up because it doesn't corrode over time, unlike the plain carbon steels. As the country started progressing, any country you take, it started from America, now it is reaching to all the countries. Slowly, as you go more on the very specialized use, just as in defense, in aerospace or in nuclear industry, you have to have a steel which can sustain a harsher environment. And one of them is the stainless steel. Now, stainless steel comes in many forms. Some people want ferritic metastatic stainless steel. Some people want austenitic stainless steel. Nowadays, we want maraging stainless steels. So many steels are coming up. Unlike other industries, in nuclear industry, the demand is growing rather much faster than the steel being, high quality steel being produced in the country. Why I tell you that? See, when you are putting any structural material inside the nuclear reactor, the high energy neutrons, protons, gamma rays, they have the power to displace atom from the lattice. As a consequence, lot of vacancies and displaced atoms they generate. These forms voids, or they generally they collect at one place, they form the voids and all. And this creates a lot of problem in the sense that they increase the hardness at the cost of the ductility, and that is called irradiation-induced hardness. So, quality of steel should be very, very pure to avoid any unwanted phase to form because of the radiation. That is one. Second is, because of the constant generation of vacancies, many of the elements started going to the grain boundaries. When they go to the grain boundary, they change the chemistry. And if the chromium concentration drops below critical value, the stainless property is compromised. A very clean steel under a very pure water should not give you stress corrosion cracking. We know all this. But in reactor, this forms under stress corrosion cracking because of the chromium has gone out of the grain boundary and gone inside the interior, and that has become the limiting factor. So now what are the factors which affect that? That is why the chemistry control is very important. Chemistry control, I mean impurity control. Okay, impurity control means silicon, it should be having very low amount of the silicon. Boron concentration as low as possible. Carbon concentration within a very limited, because we do not want even a very small tiny portion of the chromium carbide formation. Otherwise, stress corrosion cracking, you are inviting it. Now, old time we used to design the nuclear reactor for a time of suppose 30 years. Now, we are being given the task to make the reactor for 100 years. 30 years to 100 year technology is changing. That is the one field which is where I am right now still. Demand coming from the nuclear field is not being met by the indigenous steel. Generally, we end up in the imported steels. That is where stainless steel should go off, because as Professor Kamachi Modi was telling, that 2070 is marked the year of the zero carbon emission by the government of India. So old time nuclear energy was considered as another form of energy. That is, you have the redundancy in the system. You are producing electricity by coal, petrol, gas. You are also producing by nuclear energy. So nuclear energy has one issue, because it requires lot of initial amount of the investment. So private sector were not playing any role. Government can afford, so government was playing the role. That's why our, even after going nearly 30 years, 35 years of electricity production, our total, this thing is very, very low. But now government has given the mandate by 2050, we should be producing 1 terawatt electricity, which 2070 should be, means this is essential now, quasi-essential for existence, 2 terawatt of electricity. So now with this every year, on the average, next 10 years, we are going to install 700 megawatt pressurized heavy water reactors, plus PFBR, one is already next year it was planned, but in couple of years with teething trouble it will start, I have no doubt on that. But now we have to come up with new ideas also. One of them is the molten salt reactors, one of them is the gas-cooled reactors, and then fusion reactor technology is also of the way. All these require different kind of steels, particularly stainless steels. Very high quality, very controlled grain size, very low impurities, and these steels currently are generally, I am very sorry to say, but it is generally in the lab scale or in the slightly on the pilot plant stage. We do not have any factory where we can ask it and they can offer it on the constant basis. So campaign basis, some steels are being produced in the country, but the time has come to take, because now if we are going to put 1 reactor per year, our demands will be a few thousand tons. Now, in addition, there is another pressure on us because government does not want to renew the license of the coal plant. Old coal plant which are 50 years old, they will be shut down, and we have to go for the small called modular reactor, where standard things were made and everything will be cased like a model. You have a battery in a car, when the battery get discharged, you throw that battery, take the new battery out. Now, for many of these concepts, we require these high quality steels, which should not degrade. There should be provision. So you should have a very low phosphorus, very low sulfur, very low boron, and very controlled carbon. And that is, I am not talking about in the 1 or 2 ton of steel, I am talking about the 100 ton of steel. So that is the technology which is more we are waiting for. So I think in the beginning I should just say that this is the work we are going on. Yeah, thank you.
Thank you, Dr. Raghavendra Tiwari. I think very briefly, if I have to sum up, the challenges that you mentioned in the application of stainless steel in the future is on the degradation of property, probably due to the impurity segregation in the grain boundary, embrittlement of stainless steel, poor microstructure after heat treatment, and the sensitization, which is a very peculiar problem with austenitic stainless steel. These are the issues with respect to increasing application of stainless steel in the nuclear applications. But the way you explained, articulated, the opportunity is that the nuclear energy quantum is going to increase phenomenally. To reduce the carbon footprint by 2070, there is going to be large number of pressurized heavy water reactors and other nuclear power plants are coming up. So the stainless steel application in those power plants will be very good, and it will be a great opportunity for improved and better grade of stainless steels to find application in the nuclear energy. Thank you very much. I think now we will go to Dr. Gunasekaran. Dr. Gunasekaran is an expert in corrosion, coatings and cathodic protection. He is from the Naval Material Research Lab of DRDO, Defense Research and Development Organization. It is located in Ambernath. He has more than now 25 to 30 years of experience in the field, and let us listen to him and what are the challenges and opportunities that stainless steel will have in defense and aerospace applications.
Thank you, sir. As a defense scientist, our primary work is the structural materials. As far as the structural material is concerned, in India, we are having a beautiful environments, from desert to the high cold region and the marine environment. This kind of environments are not there in Western countries. They are all cold regions, and most of our defense equipments we are purchasing from them. And these systems are not functioning in our environment because of the material selections. and wrong material selections leading to the failure of the systems. And in the structural materials is concerned, 90% of the material is basically normal low alloy steels, and to some extent copper-based alloys, and very small, you can say 1 to 2% only stainless steel is there. One is actually why despite low amount of stainless steel are being used in defense is many factors. One is the non-availability of the right grades of stainless steels. Because in different sectors, we are using specific type of steels which are in a reduced quantity not available in India. We have to import it. Or the companies are not coming forward to manufacture the right stainless steels. And also the environment. A system which I'm putting one type of stainless steel in, for example, 316 or 304, it in desert and cold zones, it will work fantastic. But same time in marine zone, I cannot use that particular one because of its pitting nature. Corrosion pitting in marine is one of the serious problem. Because of that, in many places, we are unable to use stainless steels. Otherwise, stainless steels is much better one. Like duplex steels, it is possible to use it. But problem is the availability, also the machinability, again weldability is also another problem. And basically the problem is the fabrication of the systems.
Further discussions, I'm having some slides to throw where actually stainless steels are mainly used in different sectors. First, actually, I will come with the missiles, which is a lucrative items, because mainly in defense sectors, we are much ahead in missiles. I think our many types are Agni missiles are everywhere. We are internal parts, we are using stainless steels. And the main construction is basically steel, normal steel or aluminum based alloys. Here first one I'm just giving you a Dhanush series of missiles, wherein actually it is basically a solid fuel based missiles. Its body is basically a aluminum based alloys, and here it is actually the solid oxide, solid based fuels are used. Here it is mainly that the valves, especially the O fuel valves, basically Mn and chromium based alloys are particularly used. Here the problem is actually we are manufacturing it. These particular steels availability is limited because here the quantity requirement is less. That is where the problem which we are facing it. So still in Indian industry, we are able to manufacture these kind of valves and fitment. And other places, we are unable to use it. The other one is, actually both of our chairman and one more panelist are basically a nuclear scientist. Here it is actually basically nuclear submarines. We are using some portions of nuclear submarines, stainless steels we are using it. Actually, when we started it is called S series nuclear submarines. Now it is S3, S4 and S5 under our manufacturing is going on. When we started the manufacturing of nuclear submarines, 90% of the material we were importing it, and only 10% we were able to do it from India. Now in the present condition in S4 and S5, we can proudly say 90% is Indian material and 10% only we are importing it. And the main core, that nuclear reactor, is from BRC. I'm proudly say that today actually that the core is manufactured and with the help of BRC, and L&T only is manufacturing and giving all the thing because our scientists' ability to give the thing. So here it is actually in nuclear submarines, very few items, especially in the nuclear side, like reactor components, what they were talking about, and main cooling pipes and auxiliary heat exchangers, and the cycle where actually from nuclear reactor and where the heavy water is heating up, and from there normal water is getting evaporated, that is actually steam, they made steam, super steam, and it is circulating, and the blades everywhere, the stainless steels and nickel alloys are heavily used. Because of the high temperature applications, normal steels cannot be used. One of the problem which the initial one is in the roll, in the loop, only one place they have used steel, normal steel, that is low-alloy steel, is the condenser, where actually the steam, released steam after the turbine, it is getting condensed in the condenser, and again it will be pumping back to the main reactor where it is. So one of the serious problem is the corrosion of that particular condensers, because they have not used a right grade of stainless steel or titanium for that one. Because of that, it was choking. So later the design was again revised, and it has been shifted to titanium tubes. Actually, why I'm just particularly narrating all these things is use of right materials. Stainless steels and nickel alloys are right materials for these kind of systems rather than low alloy steels. So some things I'm just giving like a sodium cooling reactors. The fuel jacket material is improved, actually 316. Here actually there is no need of, when system is a 316, here the pitting corrosion is not there because of the chloride level is very, very low. So the other one is molybdenum waste, chromium 18, nickel 12 alloys. And primary coolant pipes of nuclear power plant, also of stainless steels. And fission reactors, also many type of stainless steels are getting used. That is T-purpose. Actually, Tiwari sir has rightly explained all the stainless steels with the background of how a scientist who is afraid of his wife, how he has discovered the first stainless steel. I think most of our people are in that category. So the turbine blades, again, one of the things where the high molybdenum stainless steels are used in the right place. So these are the things, stainless steels, various types of stainless steels we are using it. Even though entire submarine is basically the low alloy steel, high strength low alloy steels we are using it. But internal portions, many walls, which I'm unable to give many things because of secrecy involved in that. So rest of the things, mainly the outer hull is steel. So one of the main problem with the outer hull steel is when the submarine goes into the water, any steel, magnetic steel, produces a signature, electromagnetic signatures. So electromagnetic signatures is one of the serious problem, because any mines they can put in the water. These mines are known to sense the electromagnetic signatures from whether it's a ship or submarine, and it will just, when the submarine goes near to that, it will just explode. There is no need for the submarine or ship has to hit the mine. So that kind of systems are nowadays available, and controlling the magnetic signature is one of the serious problem. So the other alternate was, the suggested was the stainless steels. Why can't we make the entire hull like stainless steels or titanium-based alloys. One other thing, major thing is, as I was pointing out earlier, is it's a pitting nature. Most of the normal grade of stainless steels, we cannot use it because of their pitting. And when you just go for that is duplex stainless steels or super duplex, when initial one of the labs in DRDO, we started the work on duplex stainless steels almost like 2 decades before itself they started the work of entirely replacing the hull of a submarine with the duplex stainless steels. And they later, one more thing is manganese-based steels, low-alloy steels. Manganese-based low-alloy steels, strength is very low. Here it is actually the stainless steels when the work was started, and later slowly they have found out actually they are able to control the pitting nature of the steels. But there is again, welding is one of the serious problems. So when they started welding it, and later it is when the loading and cycles are started, they came to know one major aspect is the cold deformation, plastic deformation of stainless steels. This is not there in the normal structural steels. Structural steels, the cold deformation, plastic deformation takes place at high temperatures. But stainless steels and titanium alloys, this kind of problem is there. So they have abandoned that idea. Despite this kind of negative points, we are unable to use stainless steels in seawater environment. So the other one is now actually in the recent Independence Day parade, you might have seen the air independent propulsion system from Naval Material Research Laboratory, which is going to be used in submarines. See, nuclear submarine is one of the core one. Why particularly whether the nuclear submarines which we have gone is, any submarines when it is entering into a littoral water or under enemy water, it has to go inside the water for minimum 15 days. It has to hide and attack. Just I cannot go and bear, I cannot straight away attack. No, it has to hide. If anything submarine goes into the water and hiding it, minimum 15 days it has to stay. If it is more than that, it will be the happiest one. One other thing is actually the fuel which we are using is actually the oil based. It has to burn and generate the electricity to power the batteries in the submarines. For that, to start the generator, it has to come up. Because almost like every day it has to come up. When your submarine is that is in enemy territory, it cannot come up. For that purpose only, nuclear-based submarines are much more essential. But however, nuclear again is a much more green energy, but if you are handled it in proper way. In defense sectors, in defense one, when weaponry, when we are using it, there will be attacking mode, and people are there inside. When there is any leakage is there is a lot of problem for the employees, that is service personnels. So for that only, the other alternate is AIP, Air Independent Propulsion Systems. This is again one of the green energy based on fuel cells. It is fuel cells is nothing but the hydrogen and oxygen is getting reacted on the electrolyte in front of an electrolyte and get produced, electricity is getting produced. So this air independent propulsion system as a thing will have a separate oxygen tank and hydrogen source. This can be utilized by the submarine to power their batteries and stay inside the water for more than 15 days. That is a one concept which is coming up, and already we have established this one in the normal conditions, and now in the final stage of submarine trials it is starting next year. So that's why actually the particular version is shown in the last year Independence Day parade. So why I'm just particularly explaining is, here also for storing the liquid oxygen, because it is a cryogenic oxygens. We have to make it cryogenic conditions to liquefy the oxygen and store it, because as a this thing, gas cylinders, we cannot store it in submarine because of the space availability. And if you have liquid conditions you are storing, it can prolong the reaction thing. So here it is, that particular liquid oxygen tanks is basically stainless steels. It is basically 14311. This is actually particularly because of the high strength and oxidizing ability of that oxygen, stainless steels are being used. And other than that, there is actually the other source is the hydrogen source, basically. The hydrogen source, we cannot use hydrogen cylinders inside the submarine because of any small leakage, 0.4% of hydrogen comes out, it will explode. To avoid that, a solid hydrogen source is used. The solid hydrogen source is basically sodium borohydride based. So sodium borohydride based, what they will do is, actually they will, in the storage tank, sodium borohydride will be there, and in that the limited amount of water and some catalyst will be added, and sodium borohydride will react with the water and produces hydrogen. That hydrogen will be taken up to the fuel cell, and where the reaction is getting started for the electricity production. So in that particular aspect, sodium borohydride, and the catalyst is having small amount of chloride, when it is added, it produces good amount of alkali and heat. So normal steel cannot withstand that temperatures. So we have used stainless steels, and the particular structure is already been standardized, and it is in the manufacturing now. So again, I'm just coming to the back to the missiles. So not only new missiles which we are talking about, the old vintage missiles also which we have imported from Russia, still we are keeping it. Because we are not using it when war conditions are there, that stages only missiles are being used. Rest of the times, the fuel is removed and the materials will be kept. And all the fuels will be ready in ready conditions. Within 1 or 2 hours, the missiles will be ready by just loading the fuels. That is the conditions which the storage is being kept in, even in Mumbai also, we are having storage system. So in that is one of the vintage missiles is based on the oxidizing ability of fuming nitric acids. Basically, organic source and fuming nitric acid, when mixed and fired, it produces. It is very heavy missiles. Here, basically the fuming nitric acid tanks and all, basically it is stainless steel 316 based stainless steels, and also the valves inside is high chromium based. It is chromium count is around 25 to 30% of the chromium is there in that. So that kind of valves also used. Here it is one problem is actually the availability of these valves again, because missiles are there, and some of these stainless steel parts availability is not there. Now we have found out some sources from Nasik, and the manufacturing has been started, because every time we cannot import from Russia, and also Russia, this is 1980s and 90s missiles. Russians also said that we have discontinued this and we are not having any spare parts. So that actually we are, because of our industries, now we are able to survive and use this kind of missiles. So the other one is when, as a naval person, actually, when I'm just coming to the ship, major portion is basically, I was just pointing about low alloy steel. And the second thing is, very few places now we started replacing our some portions of the steels, normal steels, as well as the copper alloys with the stainless steels. Basically, since the copper alloys availability, especially cupronickel's availability, majority of the cupronickel we are importing it, NAB alloys and all we are importing it. Now slowly we are shifting to stainless steels, which is available in our environment, available by our industry. One is the propeller shaft, which is actually is being used and by the stainless steels and coated stainless steels. It is a 17.4 pH versatile manganese precipitation hardening steels. We are trying to imitate with the imported one. Initially, some failure was there because of the fracture. Now, again, there is a change in the compositions. We are able to achieve this kind of soft sign. It is in the trials and it is work is going on. And many places we are using other stainless steels in the decks, small portions which we are using it, not on the major thing. And even the main propeller shaft is basically a NAB alloy, nickel aluminum bronze alloy. That also we are planning to replace it with stainless steels, various grades. There the biggest problem is the bubble, that air bubble formation and bursting. So that kind of problems we can remove it with stainless steels. So again, fuel cells, when you're just talking about the stacks, inside the stacks also in many places we are using various type of stainless steels, and especially 304 is more than something. In phosphoric acid conditions, 304 is working very well compared to the steels, and easily availability we are using it. So not only missiles, actually the missiles launching pads basically of stainless steels, because it has to absorb the heat and non-corrosive in nature should be the lags, everything we are using as stainless steels. So stainless steels is part of our structural materials, but because of its limitation in defense work, especially for the pitting nature, and I cannot use it for particular places, but still it rules in major places like I was explaining all these things. So stainless steel is a crucial one, and how our industry is coming up with a new one, where actually, which today I'm just talking about the problem of stainless steel. Tomorrow, it may be solved by the industries. Definitely, in that conditions, stainless steel will rule the defense sectors. Thank you.
Thank you, Dr. Gunasekaran. It was, I think, wonderful compilation. You covered both the missile systems, nuclear submarine systems, and marine and naval applications, where stainless steel is playing a major role. You also detailed about the application and the various challenges and opportunities for the industry with respect to the application of stainless steel in defense and aerospace. I think if anybody asks me that what is the takeaway from this session on challenges and opportunities, I would like to give two different takeaway, two different emerging stainless steels that will have tremendous application in the future. Number one is high nitrogen stainless steels, which is one of the most versatile stainless steel that will have at economical rate, will have a tremendous property for high temperature, low temperature, and many strategic applications. Another one is nitric acid grade stainless steels that will have wonderful application, versatile application in all the chemical process plants where highly acidic environment is going to be used. Normally in stainless steel, we considered in the past that nitrogen is an impurity and keep at very low level. But in the last 2 decades, if you look at, nitrogen has been imported into stainless steel, particularly in the austenitic stainless steel. It is added up to 0.06 to 0.08% minimum, and maximum from 0.6 to 0.8%. What is the application? When you add 0.06 to 0.08% nitrogen, it helps in enhancing the resistance for sensitization and intergranular corrosion, and also it enhances the resistance to localized corrosion like pitting, crevice, and stress corrosion cracking. So this high nitrogen stainless steel is going to be replacing the conventional stainless steel, where you are demanding high corrosion resistance and also application involving resistance to sensitization and intergranular resistance. And if you look at the higher nitrogen, that is 0.6 to 0.8% nitrogen, higher levels, it has got outstanding mechanical properties. One important problem is with respect to automotive application of normal steel, is austenitic steel, is the crashworthiness. The crashworthiness is very poor because of the limited ductility with normal steels. But if you add 0.6 to 0.8% nitrogen, the crashworthiness is simply outstanding. And even this material, stainless austenitic steel with 0.6 to 0.8% is proposed for bulletproof because it has got excellent resistance for the bullet attack. So the defense armor people, for all application in tank and any other weapon system, 0.6 to 0.8% high nitrogen austenitic stainless steel and steel is today recommended for future applications. So high nitrogen, whether it is in the lower level of 0.06 to 0.08% or in the higher level of 0.6 to 0.8%, it has got tremendous potential and application, and it does not involve any additional cost in the manufacturing. And also there are many methods by which nitrogen can be introduced into the melt that will give excellent application. We have employed the 0.06 to 0.08% nitrogen austenitic stainless steel in the fast breeder reactor component manufacturing at the Department of Atomic Energy. We have fabricated, I think, almost components worth of 2,000 tons of this particular high nitrogen stainless steel, and this was manufactured primarily by the Jindal stainless steel. The other type of stainless steel that I am telling, 0.6 to 0.8% nitrogen, it is still under development. The Defense Metallurgical Research Lab and other labs in the DRDO are still working on that. But internationally, the Chinese and many other, the European countries, they use this 0.6 to 0.8% nitrogen high austenitic stainless steels for various applications in the defense and aerospace. Coming next to the nitric acid grade stainless steel, it has got outstanding property with respect to corrosion. Dr. Tiwari mentioned about the impurity elements going to the grain boundary and giving problem with respect to corrosion and embrittlement. The corrosion problem due to this impurity segregation can be eliminated if we can produce this nitric acid grade stainless steel. In this case, the impurity elements are controlled to very low level, and little increase in the chromium and little increase in the nitrogen and nickel, it gives this nitric acid resistance. So this also can be used for any other chemical process equipment without any problem. We at the Department of Atomic Energy, for the nuclear fuel recycling facility, used this nitric acid grade stainless steels to about 4,000 tons in the grade of 304L with nitric acid grade composition, and this was manufactured by the Jindal stainless. So these two stainless steels, high nitrogen stainless steel and the nitric acid grade stainless steels, are the two takeaway that if you ask me what is the opportunity for stainless steel industry in the future with respect to nuclear, defense and aerospace. I think my colleagues, Dr. Tiwari and I think Dr. Gunasekaran gave very good input on what are the challenges and opportunity of stainless steel in nuclear, defense and aerospace. If there are any specific questions from the audience, you are welcome. We are ready to, give response to that. Yes, please.
Yeah, good afternoon, gentlemen. I am Deepak Soni from REMI. We are manufacturing these stainless steel pipes and tubes for the nuclear application which Dr. Tiwari was referring to. And he mentioned about the control of the chemical composition to get the very good corrosion properties. Now, when we supply, we come to know the specification mentions there is a corrosion test. Practice C is required with a defined 10 mils per year, 15 mils per year properties are required from the 304L grade. So, okay, one thing is we are getting that steel with low impurities. When we are manufacturing a pipe or tube, what care we have to take in the process of these pipe or tube so that to meet that corrosion property of this practice C. Yeah, thank you.
Yeah. Actually, see, there are 3 or 4 basic things have to be taken care of. In most of the Indian product, the first stage of chemical composition they get. Either they get it from the imported steel or they manufacture themselves. The second problem comes in because when you are making pipes, okay, you had to do the joining, you had to do the welding. So generally our observation is that the very close, tight, the gap should be as minimum as possible. So while welding, you should have the minimum of the distortion or minimum of the residual stress. Okay, so the generally Indian pipes, whatever I've seen, the end of the pipes, they are not very close matching. While I do not know why it happens, but while cutting or something, there are always wedges and other things. And then because the welding job is done by a qualified welder who is not well educated to handle these special materials. So they weld it. And sometimes what they think, they have done extra job because they do additional run on that. But that additional rate is generating the additional stress into the material. So the material which was not supposed to go under stress corrosion cracking will start going to the stress corrosion cracking. That is the one. Second point is the surface finish. The surface finish is very much required because this becomes the problem in the later parts for the corrosion. But particularly in the pitting and other kind of corrosion, it becomes. So these two I find that Indian people, they qualify everything. Even the tests are qualified, but when it comes to final finished products, somehow we reach to all the way up to the 99%, and that 1% is become the disqualifying. So these two are the very general things, which does not require to do any rocket science and all. Okay, the third point I wanted to say is that is where we had to be very careful. The welding material, what we are using, that filler material, that is somehow still lacking in the country. We still have to, that quality material are not being produced. That is the third source. These are the 3 major sources which are creating problem. Otherwise, I generally find that most of the Indian product, at least in last 7-8 years time, they are qualifying almost all the property you can give for the testing. Yeah, thank you.
Thank you, Dr. Tiwari. I think I will also add, in addition to what Dr. Tiwari was mentioning, if you are saying about practice C and in the tube manufacturing, I think you have to give certain precaution starting from the billet stage, and from the billet to the mother tube and then to the tube drawing. See, you have to be very careful in the homogenization treatment to see that all the second phase particles are completely dissolved. Number 2 is that you have to go for checking of the inclusions, all the 4, A plus, B plus, C plus, D, and take care that it is, it is falling between 4 to 4.5. Then you get the best tube with, minimum elongated inclusions like, the manganese sulfide inclusions. Particularly, that is what is dissolving in your practice C in the nitric acid test. And that gives very high corrosion rate. So you have to control the manganese sulfide inclusion, how much that is there. So what you can do, you can take during the tube drawing, take a section of the tube and look for on the cross section how far this elongation of the manganese sulfide is taking place. All other inclusions will not play much role, but this manganese sulfide is soluble in nitric acid. So that is why in practice you may get higher corrosion rate. So subsequently you have to take care of other parameters, but homogenization, inclusion control, these two are very important, particularly if you are making tubes for nitric acid by practice. Any other query?
Dr. Tiwari mentioned about the surface finish requirement, but the specifications which we have seen doesn't mention anything specific surface finish. Maybe you can add so that we will be more careful about it. Yeah, thank you.
Thank you, thank you. Okay, if there are no more questions, I would like to thank both of my colleagues here, Dr. Tiwari and Dr. Gunasekaran, for an excellent narration on the challenges and opportunities of stainless steel in defense, aerospace and nuclear application. Thank you very much.
Well, I would just like to add on, sir, that since as a child, I wanted to see some scientists because as our families have always taught us that scientists are really, really having great intelligent minds. For that, I just want to actually say this, that definitely your ideas, your knowledge will take our India on a much higher level. A big round of applause for their immense knowledge and contribution. And now I would like to invite Raghunath sir from Virgo Communication to felicitate our moderator and panelist. So first name would be Mr. Raghuvendra Tiwari, our panelist. We are really honored to have you, sir. The next panelist, Dr. G. Gunasekaran. And now our moderator for the session, Dr. Kamachi Modali. Can I request both the panelists to please come forward for the group photo, sir?